Hello, I'm Adam Strzebonski. I'm a symbolic algorithms developer at Wolfram Research, and today I will be talking about symbolic optimization. So what's the global optimization problem? We are given an objective function, a set of constraints, and domain specifications for the variables. The variables can be either real or integers, and constraints are constructed from equations, inequalities, region element statements, using Boolean operators and quantifiers, so some variables can be quantified. And now what are the goals? We want to find the global optimum, infimum, or supremum of values of f on the solution set of constraints. So it's infimum or supremum because it may not always be attained. So it's some cases maximum or minimum if it's attained. If possible, so if the optimum is attained, we would like to find a point satisfying the constraints at which the optimum is attained. And if the function of the constraint contain parameters, we would like to find parametric formulas for the optimum value and optimum point. So I will show some of the algorithms that our global optimization is using. In recent few versions, the global optimization capabilities have been extended, and they are being extended right now. So the future versions will contain some more methods for global optimization. I will talk about this as well. So first, univariate optimization. So the most general method is the analytic method. So we would like to find all zeros of the derivative, singular points, and limits and domain endpoints, and this is enough to find the global optimum of any univariate functions. So for some classes of functions, like rational functions, xblog functions, or generally tame elementary functions, so these elementary functions that do not contain things like unrestricted tricks of unrestricted arguments, so they are guaranteed to have finite number of zeros, and we can find all those zeros, and we can find all singularities. So this class of functions, we have complete solutions. So for instance, here is an xblock function, and we can minimize it. We get solution in terms of transcendental root object. So this root object actually represents an exact number, which is a root of the function that's equal to this approximation that is shown in the last argument. And indeed, if we plot the function, we can see that we have found the global minimum. For general real analytic functions, we can solve optimization problems over bounded intervals. So in general, functions may have infinitely many zeros of the derivative or infinitely many singular points, so we are not able to find all of them in general, but over a bounded interval, we can solve the optimization problem. Here we get a message that maximize used numeric integration to show that the result is a global maximum. That means that we wanted to count the roots of the derivative, and the only way we could count the roots is by numeric integration, because the symbolic integration, contour integration for this function would not succeed. And here's the exact result again. And we can show that indeed this is the maximum. So what about other methods? So we have a class of methods using periodicity. So if a function is periodic, it's sufficient to solve the optimization problem within a single period. So for instance, here we have a function. The function itself is not periodic, but is a composition of periodic function with a function whose set of values includes a single period. So this is enough. We then know that we can just optimize the outer function over a single period, and we can solve the optimization problem. Again, we get exact solution in terms of root objects, and here's the function. It's somewhat complicated discontinuous function, but we get the global optimum. Now for combinations of periodic functions, we can also say something. So if we have a combination of periodic functions with incommensurable periods, then the maximum value is not attained, but we can still figure out what the maximum value is. And here it is. And let's show the function. Here is the maximum value. Indeed, it's not attained, but we get arbitrarily close. And the same holds for integer problems. Again, if we have combination of periodic functions with incommensurable periods over the integer, we know how to find its optimum values. Here's a minimum value over the integer, over the integers, and here's the plot. Again, it's never attained, but it's the infimum of values of the function. Other methods. So here's something that was recently added, methods using function property information. So Mathematica now has information about mathematical functions it has built in. So it knows the domain, singularities, monotonicity, limits at domain endpoint, local and global minima, and more properties. And properties can be used to solve global optimization problems. For instance, here we have composition of C integral and DOS on F, and we have information about global minima of DOS on F and monotonicity of C integral. So if we know where the global minimum of the inner function is, and we know that the outer function is increasing, then this must be the global minimum of the composition. And indeed, it is the global minimum. And here's another example that makes use of the information about global minima of Bessel J. So as we can see, Bessel J has infinitely many local minima and maxima, but we know that this first maximum is the global one. Now to multivariate optimization. So multivariate optimization is much harder. And the most general method that we have is based on cylindrical algebraic decomposition. So the advantage is it applies to arbitrary polynomial problems involving polynomial rational functions or real algebraic functions, either in objective function or in constraints. So there are no convexity requirements that are usually important for instance, for numeric methods, no degree bounds. Constraints may involve arbitrary quantifiers. There may be arbitrary parameters involved, and the method has no numerical stability problems. Well, disadvantages, there is one rather big disadvantage. It's doubly exponential complexity in the number of variables. So unfortunately, this method can be applied to very few variables, like 3 or 4. And here are a couple of examples. So here we have example with 2 variables and 2 parameters, and we get parametric solution for the maximum value. And the other example has 2 variables and 2 quantified variables. So we eliminate the 2 quantifiers and optimize over the 3 variables x, y. And here is the minimum value, which is a root object. So, okay, so suppose we don't have parameters or quantifiers in the problem, and we are not we don't really require exact solution. Is it always better to use numerical optimization? Not really. So numerical optimization algorithm and symbolic optimization algorithms are quite different, and they have quite different strengths and weaknesses. So of course, numeric optimization algorithm is better if the functions are non-polynomial or we have more variables. So these are weaknesses of the symbolic algorithm. But then weaknesses of the numeric algorithms are that if a problem is numerically unstable, then the algorithm may fail, even though the problem may be very easy for the symbolic optimization algorithm, as well as if the constraints describe a set that is very thin, then numeric algorithm may not find it, the constraint set, and may not give the correct solution. So here is an example. We take a constraint that's constructed as a product of two quadratic polynomials. One of them is squared. And so here it is, the expanded constraint, and we get this solution. And now we only change the last digit of the first number, so it's the 21st digit, and solve the maximization problem again. And as you can see, the solution is quite different, and it's in a quite different place. So the maximum, even though the difference is in the 21st digit, so certainly numerical algorithm which uses machine precision 16-digit numbers will not work here, because for 16 digits precision, both inputs look exactly the same. But even if we use high working precision, so this I ran with 1,000 digits of working precision, it takes almost half a minute, and as you can see, it's a completely different result. It's on the order of 10 to the minus 10, and the real maximum is on the order of 10,000, or is it 100,000? So it's completely different scale, completely different place. So in this case, even high precision doesn't help, and let's see why. So we cannot draw the actual set. You will see why. So instead of 10 billion here, I just use 10. So it's a similar problem, and we plot what the solution set is. So this is the first set of constraints: a very small disk and a large radius annulus, which is very narrow. And now we change the. So this is the adding the 1 to the first to this first coefficient. So we just add x squared. And what happens with the solution set? Well, it becomes quite different. So it still has the center disk, but there are really small parts only of the outer ring. So, and of course, in the actual problem that we used before, it was 10 billion rather than 10. So this was really narrow and really small disk, and really narrow ring, and this were like two small dots. And of course, the numerical algorithm couldn't find it. Actually, you can see I'm using here an internal CAD plot, which computes the plot by first locating the solution set by computing symbolic cylindrical decomposition, and then uses numeric method to draw the picture. Because if I used region plot, it would actually not find any solution for this. Okay, so let's go to other methods. So analytic methods. So they are, in some sense, they are more general than cylindrical decomposition methods. So these are methods using Lagrange multipliers or the KKT conditions. So we could find all local extrema, then pick the smallest or the largest local extremum. The thing is, we have to check the smoothness of objective functions, the smoothness and non-degeneracy of the constraints, and that's a hard problem. And then we need to check for extrema on the boundary and extrema at infinity, which again is a pretty hard and insolvable problem for most cases. So what are advantages? Well, it can solve some transcendental problems. So it can solve some problems that the previous method could not solve. However, they have to lead to systems of equations that Mathematica can solve, which are not that many for multivariate transcendental equations. So disadvantages requires abilities to solve arbitrary systems of equations and inequalities. So in general, if we run this algorithm on algebraic problems for which the previous method would apply, the equations we are getting will be harder to solve than if we just run the optimization by CAD algorithm. And so the implemented method require bounded solution sets of constraints with simple to compute boundaries and finite set of stationary and singular points. That's the case because we need to check the smoothness. We better have finite number of singularities and the finite number of local extrema to be able to solve the problem. So here's a couple of examples. So here's an example that has trigonometric functions of one variable and polynomials in the other variable, and constraints are just a box here and the constraints using the same type of functions, trigonometric for one and polynomial for the other, and we can get the solution. And the other one is we optimize xblock function over a disk, and we again get a solution. So more methods. So special case methods. Of course, linear programming is one of very important special case methods. We can solve problems with a much larger number of variables, but of course the objective function and the constraints have to be all linear. So that's a rather large restriction. But as you can see, 10 variables, almost no time. And the very close algorithm, linear fractional programming. So the objective function can be a ratio of linear functions and the constraints have to be linear. And again, problem with 10 variables, no time. And linear fractional programming, integer linear programming. So now all variables are integers and the objective functions and the constraints are linear. So here's a problem with 7 variables, and we also need to make it bounded. So the branch and bound method that's used actually can work. The unbounded problems are unsolvable. And well, we get this solution for 7 variables, and it involves quite large integers, as you can see. So now some new special case method coming soon. For evaluation of those, I used the development version. So multi-parametric linear programming, what is it? So the objective function is linear and all constraints are linear in the variables and the parameters. So we have a vector of variables x and vector of parameters t. And so the constraints, as you can see, they depend on the parameters. And let me show the result rather than evaluate. So, actually this problem could have been solved with the cylindrical decomposition method, but I tried this one and in 5 minutes it doesn't return. So that's because we have 8 variables. You have 6 variables and 2 parameters. So for cylindrical decomposition, it's 8 variables. For double exponential algorithm that sort of hits the double exponential wall, won't finish. With this special case algorithm, we just need 0.3 seconds. And here what the answer looks like. So it's the minimum value is linear function, piecewise linear function of parameters. And we could also get optimum points as linear functions of parameters. And the nice thing about the algorithm used here is that the optimum point and the optimum value are continuous functions of parameters. So that's very important in applications, that this is used in control, and so we really don't want to have jumps in the optimum point solution, because that would translate to jumps of some physical device, and that would be bad. So let's see, and this is plot of the domains of piecewise function, of the constraints for each piece of piecewise function. So on each of those polygons, we have a different formula for the solution. And here's the plot of the solution. So you can see it's piecewise linear and it's continuous. And now the other algorithm is, where did it go? Let me try. Okay. So multiparametric quadratic programming. The objective function is now quadratic in X and linear in T, but we can have coefficients in T multiplied by X. And we also require that this is a positive definite matrix, so we make sure that it is, for each value of T, we get a convex quadratic function as the objective function, and the constraints are, as before, they are linear and in X and T. So here is an example. Here is the quadratic function, the objective function, and we have the constraints which are linear and in X and T. And we can solve for minimum value in 0.56 seconds. Again, this would be solvable theoretically by cylindrical decomposition algorithm, but again, it takes a very long time. And here's the answer. So we get a piecewise function, which is piecewise quadratic. And these are the linear sets, so polygons, or in general polyhedra in parameters. So here's the picture. We have different values on all those polygons, and also on edges of the polygons and points. Some of those conditions are lower dimensional, and the white spaces where there is no solution to the constraints. And here is the plot of the answer. Actually, we get a nice smooth function. So this is a piecewise function, but piecewise quadratic function, but when you plot it, it just looks smooth. So this is coming in the future version of Mathematica. Okay, so let me show some other methods like monotonic decomposition. So now since we have information about monotonicity of many of Mathematica's special functions, well, we can see that this objective function is just a composition of monotonic function with a polynomial. So we can maximize the function, and here's the solution. And of course, these are just algebraic root objects, because eventually after removing the monotonic functions, we are just optimizing the polynomial over a polynomial condition. And here's another case. So piecewise subdivision. This is a piecewise function. If we want to optimize a piecewise function, we just optimize it separately, each piece over the condition. So this will optimize sine over the set where sine is greater than cosine, optimize cosine over the set where cosine is greater than sine. And so here's the solution, and this we can plot. So here is so this combines the periodicity with piecewise subdivision. So we just need to optimize within the single period, and within the single period we have a piecewise function. And there are many other methods that are did not mention, but so there are various heuristics that may work in some cases. And that's all. Thank you for listening. And if you have any questions, I will try to answer them now. Okay, I see first question. Are Lagrange multipliers only used when there are bounds on the variables? Right now, yes. Yes, right now, yes, because we have to have the control over the boundary of the set. So there are other cases that we may develop in the future. Like for instance, if we are able to prove that the objective function is convex, then we can allow the case which is completely unrestricted variables. So there are possible improvements to that, but right now they are used only when there are bounds on the variables. There is a question, will I post the notebook for this talk? Yes, I will post it. And I see that Oleg is raising hand. Could somebody unmute Oleg? I only have the button ask to unmute. When can the new functions be expected? So they are not going to be in the nearest version, the one that's being released right now, the version 12.2, but they should be in the next release, so probably in about 6 months, I would say. Okay, so since I see no questions, thank you very much again for attending the talk, and I will stop here.